So, so the next question that we have is the path sum problem. It is an easy tagged question, and the successful submission ratio is 46%, which is low. So, anyways, the problem is that we have to find if there is a path sum equal to target sum possibility, true or false. Is there that certain situation anywhere on the tree? And what is path sum? Path sum is the sum of the node values from root to leaf. So it's basically the path that you will use to reach the leaf from the root. Just sum all the values and check if it is equal to the target sum. So that is what the question is. So all we need to do is we have to be able to track the path from root to leaf. And what I mean by it is over here on this tree, we have leaf nodes as this one is leaf node, this one, and this one. So this 7, I have highlighted it green. So its path from root is from here, from root, then to 4, then to 11, then to 7. So if I know the path, I can easily find the sum of the values. So that is 5 plus 4 plus 11 plus 7. So it is equal to 27. And similarly for this, the path is 2, 11, 4, 5, originally highlighted in blue. So it is basically 2 plus 11 plus 4 plus 5, and that is 22. For leaf, for our third leaf over here, for this leaf 13, the path I have highlighted in yellow. So the sum is 13 plus 8 plus 5, and 13 plus 13, that's 26. And over here, the path I have highlighted in red. So that is 1 plus 4 plus 8 plus 5, and that's basically 9 plus 9, that is 18. So once we are able to somehow track the exact path from root to the leaf, we just have to be able to sum up the value and check if it matches the target value and target sum. So it is given in the question. So for this example, the target sum was 22, and therefore we had this case satisfying it, and therefore the output was true. So we return true. But if suppose the target sum was 27, again the output would have been true because this case would have satisfied it. The output would have, if had been let's say 19. So 27, 22, 26, and 18, there is no 19 possibility, and therefore the output would have been false. This would have been false. These two could have given us true for this tree. So we get the idea, right? And let's talk about how we are going to proceed and solve this problem. So if we are supposed to do the level order traversal, breadth first search, what happens is we traverse along the breadth for each level. And there is an important observation one should make, that while doing so, we completely forget whose father or ancestor was, whose ancestor was who. We just forget about that. We get lost, and that information gets lost. So the questions that demand the structure of the tree as a requirement, like the path or the ancestor from which node to which node you are going, for if that traversal knowledge is required, breadth first search will always fail you. So that is an important lesson, because breadth first search, we go from level to level, and we go from left to right and downwards. But the problem is we forget about uh, let's say this node. How did I reach this node? We have no idea, because before this we were here and we are going there. we have no idea about uh, in the above layer level, this node 13 came from which node or which parent. We have no idea. So that is why the breadth first search fails us, and depth first search very much has that speciality, you can say. So if the path structure is required, depth first search is going to be always your traversal tool, because in depth first search what we are going to do is we traverse in depth first, and you can see that we are actually traversing in path, and when we are coming back, we just have the by the traversal we see that we have the exact information of how we are traversing. So depth first search has this speciality that it can be used to keep track of the exact path from the root, and we for every node, we while we are traversing, we can see that where we are going. Okay, we reached this child, that is the left child of the previous one, so that information stays there. So we have this idea that we are going to use depth first search, and every time we hit a leaf, so the idea is that every time we hit a leaf node, what we are going to do is we are going to check the sum. If it matches the target sum, return true and stop everything. If it doesn't, just go on, move on. Check if there is other leaf on the tree that gives that satisfies the target sum. If not, check for other leaf. And if there is no leaf at all and all the leaves are exhausted, we have completely traversed the tree, then return false. There is no possibility. So that is what the logic is going to be. And now we are going to get back to our editor and code it there. So let's begin. The basic necessity requirement is that there must be a tree with at least one node. So if there is no node at all, no root, just return false. If that's not the case, we can start building our algorithm. So we will first of all define a function dfs, which will take 4 arguments: the node, which it will traverse, s, that is the sum up till now, target, that is the target sum that we want to achieve, and flag. Flag is a boolean variable which will be set to false, and which will only be triggered to true when we find that s is equal to target. And once that flag is true, we want to just get out of all the recursions and return the flag as true. So the base condition for the DFS recursion is that if the flag is equal to true, we want to return flag, that is return true. The moment the flag is true, we just want to stop everything and return true. Now, if we are on a leaf, that is if node does not have left or right child, condition for leaf, and s equal to target, which is the sum of s is the sum. So if sum is equal to target, we want to set the flag to true and return the flag. Otherwise, we will perform the typical depth first search, that if node dot left, that is if there is a left child, we will do a DFS, and DFS is returning the flag. So I'm going to store it in the flag variable and DFS, and I'm going to pass the appropriate arguments, that is node dot left will be the node. Now I will add this value of node dot left to s, target will be as it is, and flag will be as it is. Now I do the same for the right child as well. So if there is a right child, I will perform the DFS on the right child with the appropriate arguments. I'll make sure that I increment the sum by the value of that right child, adding it to s, and passing it for the further recursions or further depth. And by the way, if this recursion call, the way I'm manipulating the sum in the argument is new for you, I recommend that you take a pen paper and go through the flow of this function for a small example tree, and see how it's working, and that will give you the confidence and the insights to understand how these algorithms work. And once you get the hang of it, you'll be able to develop your own approaches for the future problems that are new to you as well. Now, we are through with the DFS function. At the end of it, we want to return the flag. Now, outside the DFS function, actually, I will just copy these base condition from here, and I'll put them all together so that it's more neat. So if not root, return false. Otherwise, return the DFS for node as starting value, that is root. Node should be perform DFS starting with root. S, that is sum, is equal to initialize to root.val, and target is equal to target sum, which is applied to the main function. And flag parameter should be by default false, and it will be only set to true when s will be at some point equal to target sum for a leaf node. So that is it. Now I'll run the program to check if there is any syntax error. Great. So let's submit and test for all the test cases. And all test cases passed. And not just that, we have the 95.98% faster performance. That's huge, unexpected, but that is it. So we have solved the problem.